So today we'll be looking at voltaic cells. So I have a diagram here illustrating a voltaic cell. So first let's define what do we mean by a voltaic cell. I have the definition here, which is you could use a voltaic cell is an electrochemical cell in which an oxidation reduction reaction chemical reaction occurs spontaneously to produce a potential difference which leads to a flow of electrons. There's a lot of things happening here. So one thing you should pick up is that in a voltaic cell, it's a spontaneous reaction. We also should realize it's a result of an oxidation reduction chemical reaction. And we end up with a potential difference which leads to a flow of electrons. So we're actually converting chemical energy to electrical energy. So that's basically what a voltaic cell does. So we're going to look at the different parts of the voltaic cell. Here we have the first portion here, oxidation and reduction here. So let's just look at this cell. This cell is actually made by having a piece of magnesium metal placed. Here's our magnesium metal. Is placed in a solution. This solution is made up of magnesium sulfate. And the next beaker here, we have a piece of copper metal, and it's placed in a solution of copper sulfate. So here our anode is magnesium and our cathode is copper. We know that at the anode we always end up with oxidation. Now oxidation, by the definition used in electron, oxidation is the loss of electron. So if you look at this reaction, we have magnesium metal lose an electron. So because we lose electron, the electron is going to be on the product portion. When we lose electron, we're going to be left with a 2 plus charge. This magnesium can be found in group 2. So magnesium is going to form a 2 plus. It's going to lose 2 electrons and form a 2 plus charge. So this is how you're going to write a typical example half equation for an oxidation. We're going to have the metal on this side. We're going to have the ions on the other side, on the product side. So the reactant side, we have the metal, and on the product portion, we have the ions. If you notice, the charges must cancel. We have 2 plus and 2 minus, so we end up with no charge. Similar to what we have no charge on this portion. Now for reduction, reduction by definition is the gain of electron. So in reduction, we have the ions on the reactant side. So that we have the copper ion gaining electron to produce copper metal. Again, the charges cancel. We have a 2 plus and 2 minus, end up with 0 charge. So if you look at this half equation, you should be able to write an oxidation half equation and a reduction half equation. Remember, oxidation half equation, we have the ions on the product side. And in reduction half equation, we have the ions on the reactant side. Okay, so in this, you may ask yourself, how can we determine which metal? Is it going to be the magnesium or is it going to be the copper? Which one of these metal is going to be the one that undergoes oxidation and which will undergo reduction? So years ago, there were some scientists who worked on this before. So we use what is called a reduction potential table. So you find it in most reference tables. They have a reduction potential, and the ones that is the metal that is further up in the series or on the table, those are the ones that are going to be oxidized, and the ones lower down is going to be the one that is going to be reduced. So based on this, we could tell that magnesium will be found further up on this table and copper will be found further down. The further apart the elements are, the greater the potential difference. So if we have two metals and they're not so far apart, the potential difference is not going to be great. So the reaction may not provide sufficient energy. If the elements are far apart, then the potential energy is going to be much larger. Okay, so we could do some practice where you will try to write an oxidation and reduction half equation. So the next thing we have is our salt bridge. So if you look at the oxidation reaction here, look at the oxidation, we lose an electron. The electron we lose here is going to travel the external circuit all the way to the voltmeter. So we have our arrow showing the electrons come inside here, and the cathode gaining an electron, the electrons are going to travel here. We have the circuit completed. So if we lose electron, we're going to have a buildup of positive charge here. And to prevent an excess of positive charge, we have what is called a salt bridge. And the salt bridge is normally made up of sodium and chloride or potassium and chloride. And we have the negative charge entering into the positive area to cancel out the buildup. And here we're losing positive charge. So we're going to put positive charge inside this portion to reduce again the buildup. So the salt bridge is to reduce a buildup of ions in both sections, half cells. And the voltmeter is here. For the voltmeter, we can actually measure the difference in the potential, and we'll see, and we have the circuit completed. If we had a bulb here, this bulb would have shown light that show that electrons are traveling. So this is a typical voltaic cell, and we can explain for oxidation, reduction, the salt bridge. Hope this helps.